In this video, we are going to be discussing the concept of congruence. Now, congruence may be a tough word to remember, but it has a pretty simple definition: having equal measures. Now, congruence can refer to things that are as simple as individual lines and angles. Lines are congruent as long as they have the same length. Angles are congruent as long as they have the same degree measure. A 135-degree angle is going to be congruent to any other 135-degree angle, no matter where it is or which direction it's facing. Now, shapes and images can also be congruent, but only if they have congruent lengths and angles. In other words, they have to be the same shape and the same size. This is different than similar, which you learned last year. Last year, when you were working with scale copies and scale drawings, you were creating images that were similar because while they had the same shape as the original, they had different sizes. In 8th grade so far, we've been working with rigid transformations. They will create congruent images to the original. And we'll discuss that again in a little bit. But first, what are some ways that we can express congruence in general? Well, one convenient way that we do it when we're looking at an image is to use hash marks. By using these hash marks, we can express congruent in shorthand without having to use numbers. For example, when we're dealing with a square, we could put down measurements for each of our side lengths, but in general terms, we can talk about all squares simply by putting a hash mark on each of the four sides. This single hash mark on each of the four sides indicates that each of these four sides has equal measure, equal length, regardless of what that length actually is. Now, with a square, we also know that it has four congruent angles, which we can just express with our 90-degree angle symbol for now. But you'll see with the parallelogram and rhombus what happens when they're not always the same. In a rectangle, same idea. We've got two pairs of congruent sides, though. So the way we exhibit two pairs of congruent sides, we know that the opposite sides are going to be the same length. But we also know that the top and bottom are going to be a different length from the two sides. So we use a double pair of hash marks to indicate the difference. The single hash marks are congruent to each other. The double hash marks are congruent to each other, but the single hash mark is not congruent to the double hash mark. That is how we indicate the difference between the pairs of congruent sides. With a parallelogram, we see the same thing get replicated. We've got the sides being congruent with each other. We've got the top and bottom being congruent with each other. However, in the parallelogram, we also have two pairs of congruent angles. These little acute angles at either end are congruent to each other, and these big fat obtuse angles on top and bottom are congruent to each other, but clearly the acute angles and obtuse angles are not congruent. So we use single hash mark to represent one pair of angles and double hash mark to represent the other pair. Same idea for rhombus, except with the rhombus, the sides are all congruent, so we can just use a single hash mark for each of the four sides. But when it comes to the angles, we have two pairs of angles, so we will use the double hash mark for them to denote the difference. So, what does congruence have to do with transformations? Specifically, the rigid transformations that we've been working on so far in 8th grade? Well, quite a lot actually, because as I mentioned on the first slide, rigid transformations do not affect congruence. And that is a core concept of rigid transformations. It's kind of the whole thing about them, is that when you perform a rigid transformation, you are not changing the congruence. Therefore, any copy of an image that is created using just rigid transformations is congruent to the original. Transformations that do affect congruence include changes that change the shape and angles, or the change in size or the lengths. So, for example, if we take this dollar bill and compare it to the original, you can clearly see that it's much bigger. By the same token, this guy is too small. Therefore, we have dollar bills that are similar to the original, but not congruent. By contrast, if we take one of these other dollar bills here, this dollar bill can be overlaid with the original simply by rotating it and turning it. Therefore, this one is congruent to the original dollar bill. We could also try this guy on for size. This one, as we can see, looks pretty different from the original, but if I flip it, no, still not there, but what if I flip it again? Now I have a copy of my dollar bill. So the easiest way to check to see if a copy is congruent to an original is to simply try and change it into the original using only rigid transformations. If you can change a copy into the original using just a change in location, a change in orientation, and or a change in direction, then you have a congruent figure to the original figure. All of these are examples of congruent figures compared to the original because they were all made using only rigid transformations.